Okay, so let's start with the second part of our afternoon session, and it's my pleasure to introduce to you Professor Cyril Closset from the University of Birmingham, and he's going to talk to us about dualities in supersymmetric quantum mechanics and DT4 invariants for quivers. Please go ahead, Cyril.
Thank you. I will start with the second part. I put in parentheses because it's a bit of an afterthought, not exactly, but first of all, it's more the subject of the meeting. But then I will start with the second part and argue why the main part about dualities in quantum mechanics with supersymmetry, which is a paper to appear very soon with my student James, is very much related to the story of DT4 invariant. What I will tell you about DT4, which is more aspirational, is more about related to work in progress with Mario De Marco and Dong Wook within the audience. So let me start with motivation then, most related to this workshop, which is about Calabi-Yau singularities and quivers of the type we already seen in several talks, especially Seba's talk this morning. So we can start our life in M theory, always a good start in 11 dimension on a Calabi-Yau n-fold. And what I'm interested in is sort of geometric engineering picture. So I'm compactifying, so to speak, in something that in a minute I will take to be non-compact to decouple gravity. And then you look at the transverse theory and you ask what's going on there in space-time. So of course, the standard and most studied case is n equals 3. So we need a threefold. Then transverse to it, you have 5 space-time dimension. And with nice canonical singularities, you get super conformal field theories in 5 dimensions. Today, we are more interested, I guess it's kind of the frontier, both in physics and math, of the case of fourfolds, where we don't know that much about the transverse space, but we know that there should be some 3D n equal 2 supersymmetric field theory, T of x4 here. And so in general, we could just consider local Calabi-Yau n-folds, but we really have in mind something more like a conical singularity if you add a metric and so on, but we don't really know very much about what's going on with the metric there. So at least algebraically, we want something like a canonical singularity that admits a Crepant resolution. So there we have the nice thing when we have a smooth model, the Crepant resolution, but there should be the blowdown there to the singularity itself. And so as I said, the case of a canonical threefold singularity, it would be a SCFT, but in general, we don't know that much. We know something like the rank of the supersymmetric field theory in various dimensions. So in 5D, 3D, and 1D here, that would be just the dimension of the number of compact devices in the resolution.
2n minus
2n minus 2, thank you. Yes, 2n minus 2, yes. So the number of in the exceptional divisor. And so that would be the number of dynamical photons in 5D and 3D, certainly. But yeah. So in the case of fourfold, as I said, not so much is known, but we know at least there is a bunch of photons and the superpartners, and we would have then some extended Coulomb range spanned by the VEF of the scalars. Extended Coulomb range means that there might be dynamical photons, which are the one which correspond to 2 cycles, which are dual to compact devices. But then in general, there are more 2 cycles in a local Calabi-Yau than 4 cycles. The difference I call F here. So R is what I call the rank, the number of devices, compact devices, while R plus F is the number of curves. And so there are all the curves which are unpaired, so to speak. So they will be dual to non-compact devices. And this gives me the flavor rank. And that would be true in any dimension in geometric engineering for any n-fold. So my putative 3D n equal 2 theories on this extended Coulomb range will have a bunch of RVPS objects, which comes in M theory from M2 and M5 branes. That's the only kind of thing we can have here. Well, almost. So we would have the particles, which are just M2 branes on curves. So they would be like GV invariant type things. Then there would be strings as well from M5 brane on surfaces. And last but not least, you can also have M5 branes on devices, which give you RVPS instantons. These last objects bring all kind of complication about whether this this field theory really has supersymmetric ground states at all. So we will just consider, for today at least, you can just think of the case. There are many such cases, even in the toric realm, of local Calabi-Yaus without exceptional devices. Something like small resolution when you might just blow up. You can have a smooth model with just curves or surfaces. Okay, and so we don't know much about the theory, as I said, in 3D, but for the perspective of, let's say, what most of you would call DT4 invariants, we don't really need to know about that. It would be nice, but we don't need it. We just need to think about these BPS objects. And as usual, instead of thinking about M theory, when we think about BPS counting, it's easier, well, it's much better to go in to look at the subspace of this object, which are just the particles that you would get from D branes in type 2A. So you would get D2 brane from the M2, you can have D4 branes from the M5 that would wrap the M theory circle. And so there you give a 2D description in space-time in which there would be BPS particles in this theory, and you would describe everything in terms of a BPS quiver, which would be the fractional brane quiver of the theory. So these three concepts are the same thing, what I call the 3D BPS quiver, which is the quiver for BPS particles from the 3D theory on a circle, which is the same as fractional brane quivers of the type pioneered by Seba and Dongwook and others in the case of toric fourfolds. And so it should be what computes also DT4 invariant of the resolved Calabi-Yau. And of course, this follows just from what I just said, the standard duality between M theory perspective and type 2A on a circle, M theory on a circle and type 2A. So that motivates us really to look at this D0 brane quiver at the singularity in much more detail. So then this BPS quiver, so the fractional brane quiver in physics term would just be D0, D2, D4, D6 bound states in general. Here, by assumption, I assume that there was no compactly supported D6. And then at a small Kähler volume, we expect, and that's something that mathematically has not been studied at all, that would be like the kind of stability, kind of Bridgeline stability and stuff like that for fourfold, that not much is known, but physically you would expect that at small volumes in the kind of very quantum regime in type 2A, there would be some, if there is still indeed a nice interpretation of this singularity, there will be the D0 brane would fractionate into fractional branes, which have an interpretation as sheaves at large volume. So there will be a description like there is in any dimension on any n-fold of at least in the G string to zero limit of D branes as objects in the derived category, so B branes.
The solution of the singularity, very smooth.
Yeah, that would be the tilde here, I guess you would. Yeah, you want the smoothing. Yeah.
Okay.
Thanks. Yes.
Thanks.
Yeah, and there are some cases when there is also a notion directly in the. For instance, if you look at orbifold, then you can think about equivalent sheaf, but in general, otherwise, yeah, we would consider the smoothing here, and consider the derived category on the smooth model. And so any BPS particle would be written as an inner combination of the fractional branes. So my D0, D2, D4 branch stay there with some number there, which will become in the point of view of this BPS brane will be just well, there is a word line in two-dimensional spacetime, and it's described by a one-dimensional GLSM with a gauge group, which will be like this, a standard quiver, unitary quiver gauge group. Okay, so these quivers, of course, they are known in many cases. In the toric case, everything is completely known. There are many interesting cases which still need to be worked out, but we know at least how to do it in principle in every cases. If you can figure out, if you have a smoothing, particular local fourfold, and there is a basis of fractional brane, that's the tricky part mathematically, right? Is there a basis that would generate the derived category? But if you know these objects, then you can just go through the machinery and compute the corresponding quivers. But yeah, in general, that's the tricky part. Someone needs to give you a quiver, and I won't do that today. But what I will discuss though is local operation in the quiver. So for instance, this will be part of a quiver. You've seen similar picture today already. So they might be, you might focus on one node and the other node might be flavor node or other gauge node in a larger quiver. And that will be what it will look like locally. I mean, there might be many incoming, outgoing arrows and so on. So let's review a bit what we have here. But we all know, most of us know that already, right? We had several talks. So I'm interested in gauge n equal to supersymmetric quantum mechanics here, important of being in one dimension only. So I have a vector multiplet, which is just a gauge field along time. It just imposes some go slow constraint, some real scalar and gauge genos, and then I can have chiral multiplets and Fermi multiplets, and they're all coupled together by the so-called, well, I will call them superpotential loosely, but the E and G terms. And so I will focus, as I said, for U1 gauge group. And then in U1 gauge group, as usual, for every U1 factor, I can have a Fayette-Ilopoulos term, which is important for the same reason it's important in ordinary quivers for stability conditions. But the new ingredient when you are in 1D compared to, let's say, 2D02, is that you can turn on a Chern-Simons term, which is just this guy, right? So a 1D Chern-Simons term, it would have a quantized Chern-Simons level, or you can call it background charge. That's the same thing in 1D. So of course, Chern-Simons, it's an abuse of notation, but that's clearly the natural generalization of a Chern-Simons theory in 1D. It's the trace over the full gauge group. So it's for every U1 factor, you would have such a guy. And the physics of it is very simple. What it does is that it shifts go slow, right? Because the gauge field in one dimension is just AT, so it's like a Lagrange multiplier. It's non-dynamical, but it imposes that you need to consider states which are gauge invariants. But if you add this term in the Lagrangian, you shift go slow, so that you would, in general, have many more states that you would have without such a Chern-Simons level, right? Because you have like more Landau levels or more whatever, more ground state with a fixed charge minus Q, for instance, to saturate this bond. In type 2A, also from the point of view of this D0 brane quivers, the freedom of turning on rather generic Chern-Simons levels is also clear. It has to do with the freedom of turning on Raman-Raman fluxes. So Raman-Raman fluxes from the West-domino action of branes will induce such a Chern-Simons level in general. And if you consider the same kind of quiver for D1 branes in type 2B, then you would have no Chern-Simons level. You can, I mean, there is no such term you can turn on that is supersymmetric in 2D. So yeah, by the way, this one, I mean, this is true in any quantum mechanics. Then by supersymmetry, I should shift that by sigma. So that will be the one term that is supersymmetric. So there is a Chern-Simons level which is supersymmetric with 2 supercharge. If you had quantum mechanics for 4 supercharge, like for threefolds, then you also have no Chern-Simons level just because it's not supersymmetric. So n equal 2 is the lowest supersymmetry, the highest supersymmetry in which you do have a quantum mechanics Chern-Simons level that you can turn on as well. So coming back to type 2A, then yeah. So all I'm saying is that you can have charge and it would generate a Chern-Simons level. In a type 2B, you could not do that because you would have a D1 brane and then there will be a tadpole condition. Like the flux has to go somewhere, but in 1D you have a D0 brane and there is still a line along which flux can go. So, or in other words, you can put a brane there and then move the brane to infinity, and you have left with flux to the left of the brane or to the right of the brane. So that is the quiver is like integrating out matter and generating Chern-Simons levels. Relatedly, n equal to quantum mechanics can have a parity anomaly in general. A correlation anomaly that is well known from this paper from the 80s. In fact, let me review that quickly. But that is just an aside, if you like, very basic things about quantizing free fields, but it's worth getting our convention right here. So here I'm doing a free chiral multiplex. So I have a chiral, I just expand the complex scalar. I mean, I expand in modes A and B with a standard permutation relation, and my fermion is quantized the usual way, psi dagger here on dicommute to 1. The supercharge. So here we are talking about a massive chiral, which which have the frequency omega, which is the mass, the real mass, where sigma is a constant, q sigma here for a charge q. And so you have those modes at frequency omega, and then depending on the sign of sigma, you have this expression for supercharges. So either the B dagger operator or the A operator appear here, for instance, times psi. And the Hamiltonian is like this. Of course, the supercharge of that commute to the supersymmetric Hamiltonian, which is Hamiltonian minus sigma times the mass times the V1 charge here. Then we can define the vacuum, but you have to be careful there about getting the right convention, so to speak. But here you can pick, let's say, the psi to be the annihilation operator when sigma is positive. So then you will need to put psi bar to be the annihilation operator when sigma is negative. The supersymmetric ground state look like this. So you just have A dagger oscillator on one side, which are like charge Q, or B dagger oscillator, which are charge minus Q when sigma is negative. And the fact that you have, so the important thing there is that this vacuum for positive and negative sigma and charge. So those will be the quantum number of the states on positive sigma and the quantum number of negative sigma. In particular, the Fermion number is shift between the two. So it will be a fermion that will be, if that is a boson, that's a fermion. And similarly, there is a background charge -1 or -q here. So in terms of the Witten index, that's what it looks like. You would have just the state 0 state with 1 oscillator, 2 oscillator, and so on. So of course, it gives a geometric series. While for negative sigma, you get the same geometric series with state the charge -1, -2, and so on. But then there is a background, what is really a background Chern-Simons level there, or a background charge that is carried by the. So in other words, you don't have a symmetry going positive and negative sigma. That is the statement of the parity anomaly. More precisely, the parity anomaly is a statement that you have a mixed anomaly between parity or charge conjugation really here and gauge invariance. So gauge invariance in that case, from the point of view of these fugacities, will be sending x to 1 over x. And this geometric series, of course, is not invariant under that. One way that people do in the literature is put this big Q here, which is a bare Chern-Simons level, to be 1/2, but that violates gauge invariance. So really, you cannot do that. Okay, so that's a bit of a review and ideology. And so going back to the question of DT4 invariance, the main things really I wanted to, there's been a lot of more thorough talks about that already in this workshop. So I really wanted to insist on the importance of 1D Chern-Simons level here. I think that will be part of the story, but this is something that is very much in progress. I don't want to say too much. So let me just summarize how we expect to get DT4 invariant from these quivers then. Of course, that's in mathematics, in principle now, it's been quite a interesting journey, but from what I can see as an external observer, almost everything is known in principle about what you need to do. I mean, there is a lot of technology that was developed by many people there, starting about 10 years ago. But there are still a lot of kind of computational, at least, and potentially conceptual, but I think those are mostly solved, but computational challenge about actually getting DT invariant for fourfolds, even local fourfolds like here, a bit more systematically, and we hope that physics can help in that. So from the point of view of these quivers and from the point of view of quantum mechanics computation, all you need to do is, okay, you fix the brane charge, the kind of charge you're interested in on your Calabi-Yau. So you fix the Chern character of your sheaf, in other words. That corresponds to a particular dimension vector of your quiver. And then you look at the kind of, the geometry of the moduli space of representations with some stability condition. The new thing in 2D in n equal 2 supersymmetry compared to n equal 4 is that I just don't have it's not just about the moduli space of representation and then I take some cohomology or intersection cohomology of that. Instead, I really have a particular coherent sheaf over the moduli space of representation. In other words, I have like some kind of bosonic moduli space and then some Fermi multiplet that naturally give me some coherent sheaf on top. And then the DT4 invariant physically should just be the Witten index or the flavored Witten index. So, I mean, that is impressionistic if everything is smooth. That should be literally this. So it's some equivariant Euler characteristic of my sheaf. And yeah, so that would be the Witten index in physics, which we know how to compute, for instance, from localization using some this seminal result by Ulrike Manier, for instance, from 11 years ago. So yeah, so that's what we hope to do systematically. And again, the insertion of like Chern-Simons levels and so on makes the story quite rich in general. Note also that everything is equivalent naturally. So here the y parameter is not the y of DT3 invariant, which would be which we don't have here. It's just literally some global symmetries that you might have corresponding to the fact that I have local Calabi-Yaus. Right. So in the following, I just want to do a warm-up for this, this routine in a case where we do understand everything, which is the simplest of quiver with a single node. There I'm losing the Calabi-Yau tree interpretation, but it's just what would happen locally when you do this kind of computation just in quantum mechanics. So in other words, what I want to do is a DT4 invariant for dummies when I don't know much about geometry or about, certainly don't know about, I certainly cannot read the 500-page paper of Joyce and so on about the mathematics. Instead, I just want to do quantum mechanics, find ground state, and see if it matches anything that mathematicians might like. So let's switch gears a tiny bit then and discuss some particular one-node quiver, so unitary gauge group, and we will study their dualities in particular, which will be that will be just.
Information like simplest non-trivial.
Where I wouldn't what?
Where you would still have some form of.
I mean, I like for what I care about, like this kind of rank 0 DT4 invariant, I would call it. I would like something. I would probably like a non-compact, like an isolated singularity. So not C4. Of course, there is always a one-node quiver which is C4 that we saw in some talks. But then to get something interesting, you need to frame. But maybe the simplest one would be something like local P1 times P1. So that's some with normal bundle or -1 twice. So that's a 4-node quiver, which somehow of 2 different types. This is the Q111 that people like. We saw in several talks. So that has 4 nodes, and that's probably the simplest one. So it has kind of similar features to the conifold, but with extra bells and results already. Yeah. Okay.
In this case, we know the 3n equals to a theory description starting from the theory application is paragraph 4.
We do not. Well, I mean, all of those cases, so that's what I would call rank 0 because there's no 6 cycles. So you can kind of count, and it looks like a bunch of chiral multiplets. But the real question is whether there is like, are there 3 chiral multiplets? Are there interaction? It looks like it's something, you know, maybe it's a 3D equal to theory that you can build from chiral multiplet, but maybe with some complicated potential, or maybe it's a more abstract theory. It's very unclear to me what we know exactly of that. Okay, so I want to consider unitary SQCD in the following, which is just the following simple theory. U1C gauge group with Chern-Simons level QC. Standard convention is that QC can be half integer, the small QC, but my bare Chern-Simons level, which is integer, is like this, related to the number of N1, N2, and N3 are the number of, N1 is the number of fundamental. So in this quiver picture, that's the fundamental multiplet, N2 is the number of anti-fundamental multiplets, and N3 is the number of Fermi multiplets, which I take to be fundamentals. You can take that to be anti-fundamental for the same price. It doesn't matter because we've seen in several talks as well, Fermis are kind of self-dual in some sense, but it's still important to declare which one you want because of treating the parity anomaly correctly. So it's a matter of convention, but you need to get it right. So here we will always take them to be fundamentals so that we know what I mean by the Chern-Simons levels. So, and then there is flavor symmetries, UN1, UN2, UN3, which each themselves can have some background charge. So those would be, this is like a dynamical Chern-Simons level. This is a flavor Chern-Simons level, Q1, Q2, Q3, but you need to keep track of them. especially, for instance, because you might want to gauge this and put it in a larger quiver later on. So this theory, if you think as a quantum mechanics with this GLSM, well, it's interesting, but it's a bit tricky because it has no normalizable ground states. So if I want to do easy quantum mechanics, I would need to lift this non-compact direction, which just comes from the fact that I have gauge invariants, which are these arrows times this arrow. So phi tilde phi tilde phi is this kind. So that's like a meson that can take a VEV semi-classically. So there is a non-compact space, and the wave function will spread. There is no way around that. So instead, we focus on this gamma SQC that was also in Seba's talk this morning. We add some gamma field, which are in the bifundamental of the flavor group, UN2 times UN1. So those are gauge invariant fields, which are there together with a cubic interaction. So the kind of loop there. So with this E term there. So in that case, it will lift this flat direction, and you get finite number of ground states, which we can actually count for any non-zero Fi terms. So that's the kind of simple problem we want to solve. And as a byproduct, we'll find dualities. So this theory has this Taylor symmetry, as I said, U11 times U13 times UN3 minus the modulo the U1, which is gauge, the overall U1. The Witten index can be computed by this Kim-Ori formula. It's just a simple GK residue. Depending on the sign of the Fi parameter, you can have different numbers. So in this simple case, those are like the contribution from the fundamentals, and these are the anti-fundamentals in the denominator. And you either pick the residues at the poles x equal y1 there, and that will be positive Fi term. If for negative Fi term, you would pick the poles at x equal y2 there, so the anti-fundamental poles, right? So that's in that case, that's what the GK residue tells you. And so in principle, well, in general, you have non-trivial result for when you compute the number of ground states for positive and negative Fi term. So you get wall crossing, which you can then capture by this index, the flavored index. By the way, in general, to keep track of everything, even in the simplest theory, it's important to keep all the, well, it's useful to keep all of the flavor parameter y. The fugacity is non-zero. If you set y to 1 there, well, you will get a number, but this number is 0 in many cases, but just because for like we'll see one reason why later, but it's certainly non-zero as a polynomial in the y's. Okay, so another bit of motivation for the project originally a couple of years ago is the following problem of finding confining models in gauge theories. So for instance, I can tell you that these two, it was discovered in kind of experimentally in a paper with one of my former students, Osama, was that this theory, so it has a particular UNC at level -1/2, 1 Fermi, NC +1 fundamental, and NC -1 anti-fundamental. This theory actually confines. So it's not obvious why here at first. It's not a naive duality at first sight, but actually it is. So that's the dual theory. So U0 meaning there is no gauge group, and you just have a bunch of mesons and fermions. So we would like to explain that. Yeah. I mean, that just means no supersymmetric ground states, and that happens in quite easily. Yeah, for instance, if NC is much bigger than N1 or N2, for instance, it's already.
So do we know like the mechanism for that? Or?
I mean, yeah.
We know it's not suicide.
You do, yeah. I mean, I'll show an example. I mean, it's a supersymmetric theory, so it's a quantum mechanics theory. So supersymmetry, dynamical symmetry breaking means just that there is no supersymmetric ground sets, and I'm just going to construct the supersymmetric ground sets. In many cases, we know that there are none, so that's what it is. There is no deeper mechanism than that, but I'll give several pictures of it, and maybe we can discuss what you mean by mechanism there. All right, so let me comment on expect first. I mean, what's the general picture? So what I will show are what are new or better understood maybe, but really new Seiberg-like dualities for this n equal to UN theory. in quantum mechanics, right? So they are infrared dualities in the same sense. So in that sense, that's why I call them Seber-like. They're kind of the simplest toy model I can think of the Seber dualities that we know and love in higher dimensions. But in quantum mechanics, infrared dualities means that the supersymmetric ground states are isomorphic, and any non-zero energy states could be whatever they are. They're certainly not isomorphic. The dualities, like the ground state themselves, depend then on the sign of the Fi parameters. So it's really a duality here that makes sense for this UN theory because they have non-zero Fi terms. And then there are really two basic dualities, as we will see, for positive and negative Fi term, which we will call a right mutation and left mutation. We can prove easily that the Witten index matches across these dualities that I'm going to write in a minute. That's a simple algebra. I mean, those are very simple residues, so you can manipulate them explicitly. And more generally, you can explicitly show that the ground states are isomorphic, so you don't even need to compute the index. We will show that the ground states are the same. So yeah, these dualities are then similar, but logically distinct from 1D n equal 4 Seber dualities or mutation, the one most common usually used in BPS counting of Calabi-Yau trefoils. So they are not, one does not follow from the other. From the point of view of n equal 2, the standard n equal 4 mutation would have adjoined, so it's a different duality. And as an operation on the generalized quiver, those are the well-known mutation operation that Seba discussed in his talk as well, and that were also known by mathematicians on so-called colored quiver or generalized quivers. But here the new crucial element, as I emphasized in the first part of the talk, is that we have Chern-Simons levels and these parity violating terms, and so we want to keep track of the transformation of these levels as well. So let me state the dualities and then derive them. So the right mutations are positive Fi terms. This is the duality move for these so-called gamma SQCD, so with the gamma field. So we've seen this picture before. But yeah, the Chern-Simons level QC becomes minus QC. It flips like this, and the flavor term adjacent to it flips in that way. Of course, it's related also to kind of cluster-like transformations. The left mutation similar, then you go in the other direction. So sorry, I should have said, importantly, the dual gauge group is UN1 minus NC. So you flip, in other words, in this mutation, you flip the fundamental arrow, and then you get the number of fundamental minus NC as a dual group. In the left mutation, you flip the anti-fundamental arrow, but that's what you should do if you have negative Fi term. And then you get UN2 minus NC as a dual group, and again, you flip the Chern-Simons level as well to the minus Q. Sometimes, so those are the duality that always exists for SQCD. Now, sometimes you can do a bit better in the sense that they could be trivial wall crossing, which means that they're really an isomorphism of the wave function as you cross, right? So those are very special systems where, in a sense, the ground state actually makes sense for zero Fi term. And so you can literally, in that case, without wall crossing, the wave function that you would have for positive Fi terms can be mapped to the one negative Fi term continuously without losing anything at infinity. So if you have trivial wall crossing, then you can combine trivial wall crossing, which means flipping the sign of the Fi terms, together with the dualities to get extra leverage. So there is a sufficient, I believe, probably necessary condition, but certainly a sufficient set of conditions for trivial wall crossing, which is that the Chern-Simons level, small qc here, is in between a plus 1 and minus a minus 1, where a is this half integer, which is 1/2 n1 plus n2 minus n3. So number of Karelman, number of Fermis, minus the number of colors. And this is, I call it A because that would be what the anomaly in a D1 Brent system, I mean in 2 dimension. But in 1 dimension, that's just a number. And so if you can combine this with wall crossing, then you can do several dualities, right? Because you can go on one direction and the other at the same time. So for instance, so it means that this theory and this theory from left mutation, right mutation are actually equivalent. But that's a non-trivial statement. So in the special case, for instance, of A equal to 0, then QC has to be 0, and then you recover the triality of Gade, Kukov, and Putrov. Or that's how we were just first started looking at it. It's just 1D reduction of these trialities. Okay, so that explains my earlier statement about confinement as well. So in these particular theories, I can do I can go from there to there in 2 steps. First, I flip these arrows there. So this I go from UNC theory to U1 theory, but now it has negative Fi term. But now this theory had a non-trivial wall crossing, so I could only go in that direction. But this new theory, it's an abelian theory, U1, but it has trivial wall crossing. And so now I can flip without any loss the Fi term there, and then again dualize, and now I get the confined theory. So I'm using the duality twice together with trivial wall crossing statement. So in that way, you can find all kind of nice trialities that are useful in other contexts as well. So let me first, we will then analyze this quantum mechanics for UNC in two ways. First on the kind of X branch and Coulomb branch using QFT language. So let's look on the X branch, meaning I'll consider here positive and really large positive Fi parameter. And then we will consider the case of N1 larger or equal than NC, because otherwise by the right mutation, right, if N1 was smaller than NC, then the dual theory would be negative gauge group. In other words, there would not be anything, but that will be SUSY breaking. In that case, there is no ground state. So we take that case. Then the 1D GLSM flows to a nonlinear sigma model in 1D where the following target space. So again, we get a bosonic moduli space and some bundle over it. So the kind of base of the target is a Grassmannian. Standard takes this quiver by itself, NC with N1 flavor, it gives the Grassmannian in a GLSM always. So NC planes inside CN1, C to the N1, yes. But then, so that means that from the D term, essentially, you need to give a VEF to the field phi, these arrows there, which will be N1 times NC matrix, which needs to have maximal rank, NC. But the real question is, what is the vector bundle E plus that you obtain with this particular matter content and Chern-Simons level? So the answer is this bundle. So let me explain how it comes about. So first, a bit of notation. On the Grassmannian, there is a standard tautological bundle S, which is a rank. So for the Grassmannian of GR NCN1, of NC plane inside CN1, then there is a tautological bundle, which is the bundle where the fiber are the particular NC plane at that point on the Grassmannian. And then there is a quotient bundle, which is the co-kernel of the insertion of the tautological bundle inside of the trivial bundle C to the N1. In other words, that's like looking at the orthogonal plane to the transverse to that point. So they're related in that exact sequence, the Euler sequence. So why do I have this bundle? Okay, there are 3 pieces. One from the Chern-Simons level. So it inserts this line bundle det of S to the QC. That the physical reason is that really it modifies the Gauss law. So yeah, let's see, the one for N3. So that comes from the Fermi multiplet. That's the easiest one. You have fundamental Fermis. They are valued naturally in S just because they are in the fundamentals. So that pretty much the same as saying that they're valued in the tautological bundle. There are N3 of them, so you take N copies, but now you need to take the full fermionic Fock space, so the full fermionic, so the full exterior algebra of these bundles. And similarly here, those will be the contributions from the anti-fundamentals. So the anti-fundamental by themselves, they be valued in the dual of the tautological bundle, but that's not what we have here, because I have the combination of the anti-fundamental together with the neutral Fermis, which are paired like this in the superpotential. But this phi we say has maximal rank. So what that does is two things. First, because of this condition, it sets all the phi tilde, so the anti-fundamental, to 0. But then this guy this VEF for the phi, so because we are on the Grassmannian, gives a mass to all of the phi tilde and most of the gamma fields. The gamma fields which are massless are the ones which are orthogonal to phi tilde. In other words, they're valued in the quotient bundle, or it's dual here if you are careful with the orientation. So then the ground state of the quantum mechanics should just be the standard story of Witten from before I was born. The ground state will be in the cohomology of the target space, more precisely of the Schiff cohomology of this target. And okay, so that's computation you need to do. But in this case, on the Grassmannian, everything is known. You take a textbook on Grassmannian, you learn a bit about Schur functors and Borel. I will do that very quickly here. Let's see. We don't need too much except to say that for my bundle of this type, so the exterior algebras of some bundle with m copies, there is a nice extension in terms of Young tableau and a Chern functor of the bundle. So Chern functor is like you take some particular symmetrization and anti-symmetrization according to Young tableau of a bundle to get a bundle whose fiber have the dimension of the representation lambda, where lambda would be some highest weight for some SLN symmetry, right? So you get this nice expansion. And so you can re-expand my E plus bundle like this. And so all I need to compute are the cohomology of this non-trivial bundle F, which is here. So some particular Schur functor bundles of Q and S. And the latter can be computed using the Borel-Weil-Bott theorem. The details don't matter too much, except that we have explicit formula that just depends on a bunch of Young tableaus, lambda and mu that need to be in some. So lambda y of n m, it just means that you have a rectangle n times m, and you look at all the Young tableaus in this rectangle. So you sum over all these Young tableaux. There is a condition that from lambda and m you form this omega here that needs to be so-called regular, and that's an explicit formula. So completely explicit formula for the cohomology. So those are the ground states. In particular, you can compute the Witten index by just looking at the Euler characteristic of this cohomology, or really some equivalent version. Here, by equivalent, it will mean that given some vector space here in the cohomology that comes from some particular flavor symmetries, you would consider the corresponding Schur polynomial to be its equivalent dimension. When you set y to 1, that's just the dimension of the vector space. And so you get an expansion of the index in terms of Schur polynomials in the fugacities for the flavor symmetry y1, y2, y3, completely explicit, finite polynomial, unlike the index of GK residue formula, which is not obviously finite, but of course, you can check that they match in all examples. Well, we did a physicist proof that they match by computing 1,000 example in Mathematica. I'm sure there is a better proof. Okay, so you can also go to the other phase, negative Fi term, very similar story, but now you get a Grassmannian in CN2, NC plane in CN2, and a similar bundle. You have to be careful with the orientation and so on, but it's all very nice. Here we know everything, okay? And so then the duality there is a statement very similar to, well, it's following some similar discussion in the 2D dualities by G.A. Sharp and Yu 10 years ago. It's related to the standard Grassmannian duality, right? You have a NC plane in N1. There is an isomorphism with the Grassmannian N1 minus NC when you map the plane to the NC plane to the orthogonal plane, and so that at the level of the bundle, the pullback of this isomorphism map S to Q dual and Q to S dual. And so when you apply to this and that with the particular map of parameters and flavor parameters in my dualities, you can check that on the nose, including all signs and so on, by the way, including the Fermat number mapping, they map exactly. So by the way, when I should have mentioned, when I say sign, all this bundle come with all signs, including this extra algebra, I take the sign. In other words, those bundles are really K-theory classes, right?
Data is the difference between plus in E minus or the bundles?
Zeta, yes. So my
Yeah, so-
yeah, so I have different. So if I fix my gamma SQCD, so UNC is fixed, then I have two phases, positive and negative Fi term, zeta. So yeah, then I have different geometries and different bundles, both the geometry, both the base and the I, because in yeah. So going back to yeah. So for positive Fi term, then this one is the core Grassmannian, and then the other guys gives the bundle. While on the other, for negative Fi term, you take these two to be the core Grassmannian, while the other two gives
I
the
see.
bundle.
And then what happened to the Chern-Simons term?
Yeah,
This
those
discussion?
are the
The Chern-Simons terms, so that's my big QC, which is so it just gives a particular line bundle in it's an extra line.
Also the line bundle.
It's an extra line bundle, the determinant of the Toshika bundle is the purpose.
Oh.
Yeah, so you get that, and in the negative Fi term, you get essentially the same. Yes, is that with the dual? So it's really like minus QC, but that's a matter of because you map the you change the version of the arrows, so what you was S become S dual and so on. And that will be important to then just prove this. So this is just plugging the parameters between the dual theory, where in the dual theory now what was NC is now N1 minus NC. The flavor symmetry have been rotated. I mean the parameters. You plug in that in, and then you map that those two are mapped with the Grassmannian duality. So it's literally an isomorphism of target space. So then in particular the cohomology is the same, the index is the same, and so on. So that proves the duality at the level of the nonlinear sigma model. So okay, that's nice. As far as I know, that
The quantum mechanics is the only case where I can really prove the dualities at the level of states instead of just the indices. Right, in higher dimension, we rely on partial functions. But here, there is no excuse. It's quantum mechanics. You should be able to understand everything. So that's what we wanted to do.
This discussion of some 3D series said you're worried about the quantum version might modify the property modular space and all that. So somehow in this case it's much in the classical space. So you expect that this classical much of the modular space will persist even after all these quantum versions are taken account. Is that what you expect?
yes, I mean this is different phases. Right? So what this is like taking a large Fi term in one direction and the other.
Yes.
So it's semi-classical, even in the quantum mechanics. I can integrate out my
In the
I
in the
believe
large
mechanism in large Fi term.
Hmm.
So those are large Fi term phase.
Okay.
In fact, let me discuss the small Fi term phase in a second. Would be the Coulomb phase. But then yeah, we expect everything to be continuous.
Okay.
But yeah.
So yeah, so perturbative ground states in gamma SQCD. So there will be some interesting subtlety, but yeah, there is a very interesting scaling, which was the one used precisely for localization computation purpose, for instance, in this seminal paper, which is when you take very small Fi term, very close to the wall, but at the same time you let the gauge coupling run it runs very fast in one dimension, the gauge coupling, but so it goes to infinity, but you keep this particular G times zeta fixed. That's the Coulomb range scaling. Right? So it's kind of a fine tuning when you try to hover near the wall of marginal stability and find an approximate ground state there. That's the idea. So we can analyze the perturbative ground state in that picture. So in that picture, unlike the X branch where you just integrate out the vector multiplet exactly, here is the other way around. What we want to do is integrate out the chiral multiplet and have an effective field theory for the vector multiplet near the wall. So the picture you analyze the ground state perturbatively is as follows. You first assume that sigma, or in general the masses that you might have, is different from 0. Then, as I reviewed in the case of free chirals, you have free theories of chiral and Fermi multiplets. And so, okay, you quantize them. It's just a simple Fock state of fermion bosons. And you just need to impose Gauss law, right? The modified Gauss law with the Chern-Simons level. So those are the physical states in that theory. But now the sigma itself is dynamical. It comes from the vector multiplet. So here you already integrated out AT, which was just a Lagrange multiplier. But now you need to do the path integral, so to speak, or just quantize sigma and the gaugino. But that's a particular effective field theory that, at least precisely in that scaling, would be this simple action, which is a classical action studied by Witten in the similar paper on quantum mechanics and Morse theory in 81. So it's a standard action. I mean, you can analyze this for any potential. It's a real potential H. So the scalar potential is h prime squared, right? And in that case, we will compute it in a minute. And finally, in my gamma SQCD term theory, there is this E-term interaction that you need to. So this is free theory. This is this effective field theory. You also need to take into account this E-term that you will do in perturbation theory. So this is free, but then you can look which states are lifted by the perturbatively by the E-term. It will lift infinite number of states in general. So the effective superpotential for my for my sigma field is as follows. It's just a one loop computation, really. It's a standard log type thing from a path integral point of view. So it means that I have examples of potentials like this, 1 over absolute value of sigma. That's the kind of potential we have. Then in any of these quantum mechanics are essentially, you know, if you just take that as the full theory, not as an effective theory, then there is, you know, the exact ground state. That's the beauty of supersymmetric quantum mechanics. It has, it's a particular wave function of sigma, which is e to the e or e to the minus e. And it will be, in our case, you think of it as being valid near a critical point of the superpotential, and it will be normalizable. One or the other will be normalizable depending on whether it's the second derivative is positive or negative. So it's you know, the one side or the other in H. And the difference between the two is that one has a Gaugino insertion between the two, so that they have different. If one is a boson, the other is a fermion, so that's important. Okay, so in that way, we end up with a finite number of perturbative ground states which are localized near the critical point. Here is a schematic picture. So in blue would be some potential. Typically, it would have some divergence at various points where really because this potential is obtained by integrated out chiral multiplets, but at some point on the sigma, this is the sigma line, at some point the chiral multiplet will actually be massless, and so you get a diverging energy that's expected. But then near this critical point, so zero energy there, there might be a normalizable wave function, like in this case. There might be two different states. So what often happens, so then you look at each critical point and you count the perturbative ground states, right? Now, what often happens is that you have pairs of ground states, like this one and this one, for instance, which actually have the same quantum numbers, or for all the flavor symmetries and so on, but differ by a lambda insertion. One is a boson, one is a fermion. So in this kind of, if you take this potential seriously, then they're just by themselves, you know, they cannot move because there is infinite potential energy between the two. But we know that this is an effective potential. So clearly at the energy MC, the Coulomb scale, you don't know what's happening up there, right? So the potential is only valid near critical points. But if I naively just cap this kind of, you know, infinite wells, so that it looks like a smooth potential, then I would have actually an instanton that goes from there to there. And so the true ground state would be a linear combination of the two. And well, in that case, it would actually lift both states in this case. That's a standard computation again from Witten, precisely in this situation with a lambda insertion between the two. So we need to conjecture that because here it's an only effective field theory, but if you look at the full GLSM, there will be an instanton-like correction to my perturbative results that would lift this pair state, right? So if I do that, we exactly match the X branch the description. At least we did that analysis systematically for U1 so far. There is a similar story for non-abelian case actually. So let me finish with an example to illustrate this. So take a abelian theory U1 at level KC with just two fundamental and one anti-fundamental, no Fermi. So in that case, the target space is just a P1, very simple. And the tautological bundle is O minus 1 in that case, and so is Q tilde. So this is a very simple geometry for the bundle. I just this two term. I have plus O of minus Q and minus O of minus Q minus 1. The cohomology of this of OL on P1 is very simple as well. You get global section if L is positive or non-negative. Well, and it's minus 1. There are no cohomology, and there is a H1 cohomology if L is smaller than minus 2. So in this case, okay, let me take QC equal 2 for concreteness. I have then those two contributions. The cohomology are both H1 type. One is a fermion, the other is a boson. There is one fermion and two bosons. Indeed, you compute the index by whatever method you like, you find this guy. Okay, so three states. One of them is this C2 is in a doublet of the SU2 symmetry here for that rotates the flavors, the fundamentals, and this is like the determinant representation of SU2. So you can compute everything from what I said so far. If I wanted to reproduce that from the Coulomb range analysis, I look at this potential. Those would be, you can look at the perturbative ground states. There are infinite number of them because they are mesons, but most of the mesons are lifted by the E terms in perturbation theory at one loop. And then we find 5 perturbative states on the Coulomb range. This is the kind of picture there. There will be 4 states there and 1 state here or something like that. So those are the perturbative states. If I write in terms of the index, they will look like this and like this. So the conjecture here is that this contribution, they cancel each other. I mean, they cancel each other in the index. That's a fact. But the idea is that the ground state themselves will have energy, which is e to the minus something, some instantaneous contribution. So that's what should happen. Let me finish with an interesting comment about this from the point of view of the GK residue and really the meaning of the GK residue. In this simple example, this is the GK residue formula. So that's a simple integral where you need to pick the poles at x equal y11 and y12 and sum them up. Then when you do that, you get, of course, the index here. But if I instead pick the poles at x equal infinity, which is like going to sigma very negative, that will be looking at there, then I would pick precisely those naive perturbative ground state there. So I would reproduce precisely this contribution here at sigma negative, while for sigma between minus m and m, I would get similarly, that would correspond to picking the residue at the anti-fundamental, so this residue. And in principle, I would pick the residue also at x equal to 0, which is sigma plus infinity, sorry, but in that case, it vanishes. So this is a general lesson. The perturbative states can be obtained from the kind of path integral there. I mean, this GK type residue. But instead of looking at GK residue, you look independently at, I mean, here in the Abelian case, you can, of course, I just deform the contour into, instead of picking this residue, I pick the other residues, right? So that's a mathematical identity. But I'm saying that the contribution from the different one will be precisely the perturbative ground state in various sector. And that's quite intuitive because doing that, for instance, for sigma minus infinity, so looking at the residue around x equal infinity, that's precisely what you would naively do if you expand something. So that would be, let me go back to actually, when I consider the chiral multiplets. Right, if you quantize the chiral multiplet for sigma negative, you get an expansion like this essentially, and then you would, picking, looking at the residue I just took is like taking the x to the 0 components. It's like imposing Gauss law. Yeah. So you impose Gauss law, but you impose Gauss law differently at sigma positive, negative, and so on. And that's precisely what you would do. So that's reproduce the naive perturbative states. And so it's tempting to conclude that this more mysterious to me still GK residue prescription like is repackaging all the perturbative states on my Coulomb range analysis, including what would be non-perturbative corrections to actually get the exact ground states. So that concludes it. Let me summarize what I just said. We studied at n equal to supersymmetric quantum mechanics, and I wanted to emphasize the effect of 1D Chern-Simons level, or general the kind of chiral effects compared to 2-dimension for the same kind of quivers. And what we did is establish really this basic duality move or mutations of 1D n equal to unitary gauge groups. So of course, in the future, there are many obvious generalizations that are interesting to explore. Generalized quivers are less obvious to me. I mean, of course, it's tempting to say that now we have the basic move, and then you do that in a larger quiver. But if you think in terms of just basic geometry, it's not at all obvious that the Grassmannian duality generalizes when you embed that in a much more complicated geometry from a quiver. So you can study, for instance, just simple flat quiver and so on and see what happens there, geometric.
Common levels of the canal, like some Calabi-Yau 5 all layer or something.
Yeah, there could be many. And then, of course, I think it would be very interesting to also look at the non-unitary gauge groups and maybe also with supersymmetry, in fact, right? As I said many times to my student, there is no excuse not to understand everything because it's quantum mechanics, right? So you can, we should similarly look at dualities for 1D and equal 1 quantum mechanics, which are quite interesting. They don't have written in text, but they have. Okay, so yeah, so finally, what I started with is that the aspiration of this kind of simple-minded investigation is to really understand complicated mathematics in a way that doesn't break my brain. So doing quantum mechanics, that's something I can explain to kids or to myself. So thank you.
Peter, for the very interesting talk. Any questions? No more questions?
Yeah, to some extent, for the final comment, like so the deriving the DT4 from quantum mechanics, that's partly what we did with Rak and Rak-Kyeong, right? So try to start with the JK-4 3D quantum mechanics and derive the expressions in crystals and associated invariants. So of course we didn't have the Chern-Simons term, and it's unfortunately there were not too many expressions, known expressions in mathematics to compare with.
Yeah.
So we get a lot of complicated formulas, but then it's just complicated to some extent, and so unpacking that remains to be done. Yeah, I think that you have a lot of geometry under control. So
yeah, that was the idea.
So probably, yeah. I mean, we evaluated it, but it doesn't mean
what you did was mostly for like some frame quiver, right? And some.
Yeah, that's right.
Yeah. Well, yeah. For me, the simplest thing I have in mind is like DT4, like rank 0, DT4 invariant, so to speak. Well, yeah, there are situations where simple situation like this one and so on, when you can literally understand moduli space from the point of view of the brains and so on, and what they should look like, and try to. But yeah, that's very much work in progress. But yeah, I know that there's been a lot of work by you, by Seba, and so on.
So is there some classification of this more realistic figures?
Classification, what do you mean?
Well, some set of simple, relatively simple geometries for which you can find.
Yeah, well, I mean, the historic case, you can write the number of things which are simple in the sense of contain only 4 nodes is rather small. In a different project with Andres Pagliucci and others, we were looking at, I think that there are others, but they are non-toric. And there are various models of like things where you would only have curved, like some sort of Copan-Duval type things in 4 dimension. So we're trying to see which one would have this kind of non-Crepin commutative resolution. But yeah, so far no classification.
Okay. Yeah. No more questions. Let's thank Cyril again.